He is currently working as an associate professor in the Department of Mechanical Engineering at the IIT Palakkad. He holds a PhD in Metallurgical and Material Science Engineering from IIT Madras and strong academic background in mechanical and material engineering. His research interests include additive manufacturing, fatigue, fracture, and failure analysis. Prior to, he also joined in IIT Palakkad. He worked with GE Global Research and NBC bearings in various research and engineering roles. He has also held several important administrative positions at IIT Palakkad, including Associate Dean of Administration and Chairman of PG admissions. He has received notable recognition such as Institution Medal for the Best PhD thesis from IIT Madras and a Patent and Innovation Award from GE Global Research. Today, for us, he going to deliver a session on metal additive manufacturing for implants. With this short introduction, I hand over this session to Sir Dr. Kesavan to give us pitch.
Okay, thank you. I have planned to give a brief talk on processing and characterization of additively manufactured titanium alloy, that is titanium 6 aluminum 4 vanadium for biomedical applications. I hope my voice is clear and audible. Is that fine?
Yes, sir.
Yes, sir. Okay. The content as follows. So I'll start, with giving the overview of our institute and in general, generic materials that are used in biomedical applications, and brief introduction about additive manufacturing and what are the challenges. Then why certain materials that requires heat treatment after processing through additive manufacturing. At the end, I'll also briefly touch upon metamaterials, which is recently mostly processed, and good amount of research is conducting on metamaterials. Right. At the end, I'll briefly touch upon metamaterials. Then I'll make a summary. You can actually interrupt in between if you need any, if you have any questions or clarifications. Otherwise, also fine. We can discuss at the end. To start with our institute comes under third generation IIT, which was established in 2015. Currently, we are almost almost 150 or 140 faculties and students strength across 1,400. And there are a good number of PhD scholars, right, at our institute. And the number of PhD scholars are almost like equal to the MTech at present. So, which means we are doing a good amount of, or we are very active in research. Uh, this is the aerial view of IIT Palakkad, and if you happen to travel in and around Coimbatore, or if you are entering to
Recording in
Kerala,
progress.
please visit IIT Palakkad, and what you are seeing is the aerial view of our institute, which is located right under the foothill of Sayatri. And of course, we are having good amount of international relations with the various universities across the globe. And as far as the departments are concerned, we have 7 engineering departments and 3 science departments, and 1 humanities departments. As far as the courses in BTech, there are 5 courses, and in MTech there are 10 courses, and in MSS we offer actually 3 courses. coming to the biomedical implants, the biomedical implants, it has a specific, kind of, meaning. Either it is a natural or synthetic material, which are, designed to interact with our human biological systems, right? So mostly for purposes like diagnosis, treatment, repair, or replacement of tissues and organs. Okay, so and these implant materials are major subset of biomedical materials, and they are specifically designed for long-term interactions with the body in used in medical applications. So the purpose is they should support and replace biological structures. And if you look at the mostly used components are the material spots in biomedical applications, we can see that in a cranial implant, mostly used materials are titanium, right? It's either we call it as a CP titanium, which is commercially pure titanium, or a titanium alloy. To an extent, we use titanium 6 aluminum and 4 vanadium. There are conventional materials like stainless steels are also used, but considering the high strength to weight ratio, the titaniums are mostly preferred. Right? When it comes to the coronary artery stent, so mostly used materials are cobalt chrome or sometimes shared memory alloys, which is also called nitinol alloys, and conventional materials again stainless steels, right? And if you look at both joint replacement, either it can be total hip replacement or total knee replacement. Mostly used materials are again cobalt chrome, titanium, and conventional material is stainless steel. Okay? And if it is bone fracture implant, mostly cobalt chrome, titanium. So if you look at in general, the mostly used material, conventional materials are stainless steel, right? And if you look at other materials other than stainless steel, titanium is preferred, and next to titanium, copper is used, right? And comparing to these materials, so titanium materials play a very important role because of its high strength to weight ratio. Okay, so these days the research with respect to titanium, 6 aluminum, more vanadium materials is rising up, and particularly people started focusing on processing this material with additive manufacturing, 3D printing. Okay, if you look at the implants, the global scenario, the millions of people they suffer from bone fractures, of course, and the current implants, right? As mentioned, stainless steel, copper from titanium alloys, and they dominate almost like 40% of the market, mostly, right? And going forward, so 2030 is the revision surgeries research, and the knee revision, revisions will be increased, and hip revisions will also be increased. Okay. Uh, and if you look at the among the populations based on the anatomy, if you see annual orthoplasty numbers, it is keep increasing. That is true with other orthoplasties, right? So for both men and women, it is increasing. So particularly if you take the orthoplasties for the knee and hip, right, and they contribute more compared to shoulders, fingers, and others, right? This is as far as Japan population study. Similarly, for US population study, so the trend is increasing, right? So the number of the procedures or the orthoplasty is increased, increasing the years, right? And then of course we look at the hip and implant usage. is also actually increasing it. Right? This is the scenario global, right? So I've just shown here example for Japanese and US population study. Right. So if you look at how these components are implants failed, right? So let us understand how actually, what are the different failures one can expect or normally it takes place, right? Implant failures. So mostly infection. So sometimes infection, will cause the implant failure. So like bone infections, right? So that lead to implant failure and loosening. So we call it aseptic loosening. Okay. So what happens when there is a loosening? There will be a interface slip taking place between the implants or implants with the bone and any other interfaces, right? So the loosening will take place. Once there is a loosening, so there will be a swelling. Okay, so this is another types of failure. And another very important failure is we call it as a synovitis, right? The synovitis, basically, it is bulge actually, right? So the bulging will take place and stress shielding, right? So when there is a mismatch in the mechanical properties, normally that leads to stress shielding, right? So you can find that when the stress is shielded, so that will be a kind of bulging, and of course there's a wear and corrosion as well, right? So when there is a wear and corrosion, the metal parts which are coming out, due to the wear process, and that will actually get into the human biological systems, or sometimes they stuck in between uh, the contact that lead to a severe pain. Right, these are all the commonly seen implant failures. Okay, so now that's one thing. And the second thing, if you look at the structure of the bone, the structure of the bone, it is completely porous in nature, and it is not uniform porous. It is kind of gradient porous, which means at the core of the bone, which we call it's a cancellous bone, have a high porous, and when it comes to cortical bone, it is low porous, which means denser at the surface and more porous at the core, right? And the amount of porosity and the variation in the porosity that varies, right? Male to female and adult, child adult to aged population, right? But the point is, any bone structure we take, it has actually gradient in porous structure. Okay, so this is how it looks. How the porosity will change or looks at the surface and the core. Okay, and if you look at the properties, as mentioned, if you see the cortical bone, the cortical bone Young's modulus is varying between 10 to 30 GPa, whereas its density is 1.6 to 2 gram per centimeter cube. As mentioned, so mostly used materials are stainless steel, and in stainless steel, austenitic stainless steel, and the normal grade is 316L. If you compare the bone properties with the stainless steel properties, there is a huge difference, with respect to the mechanical properties. That's what actually mostly that leads to stress shielding, right? There is a huge difference in mechanical properties. Okay. So if you compare the bone properties now with the titanium material, so there is almost you can say that it has a less density, but Young's modulus is higher when compared to the bone. Okay, but still it is lesser when compared to steel, but still it is considerable. Okay, so this is the reason titanium 6 or titanium materials are mostly used. Still, you can compare this with the CP titanium. And if you take the magnesium alloys, right, you can compare the magnesium alloys, the density of the magnesium alloy is almost close to the bone. So that's the reason. So there is another big another area where people are actually working on magnesium materials, right? Because the magnesium mechanical properties are very close to our density. In other words, is very close to the bone density. Okay, right. So these are the various materials that are used for biomedical applications, and you can see that the bone density is lowest, whereas the material like stainless steel and power chrome, that density is higher. Why we have to worry about this? Higher the density, the patient will feel the heavier the component. They even the bone will not feel like uh, the properties is matching. So that's what, as mentioned, if there are any issues that lead to stress shielding. Okay. And these are all, again, the materials used like CP titanium, Ti64. There are various category of titanium and power chrome materials categories, right? So used in biomedical applications, right? Okay. So if you look into this titanium alloys, the titanium alloys, there are three major categories: alpha, alpha plus beta, and beta type. And this Ti64 is comes under alpha plus beta alloy, right? So the advantage of this Ti64, as mentioned, low density and low bearing stability and very good biocompatibility. And it also has a very good corrosion resistance and high strength to weight ratio, right? So these are all actually some of the advantages, and you can see that the research trend of surface development on titanium alloys, right? So now these alloys or titanium materials are not used as such. Okay, when I say not used as such, in the sense it is not as processed component fit into the human body. Its surface has to be treated. Okay, and you can see here on the right hand side. So there are no different generation or processes that are actually applied on these materials. Okay, so usually polishing is done. Okay, so before they actually put into the human body, polishing it's a kind of general roughing. We classify them as a first generation surface preparation. And recently, if you look at there is biological surfaces, right? So the recent advancement is that we can even actually coat some of like biological tissues or stem cells on the material before we put into human body, right? So in between, you can see there are other processes like develop functional surfaces like anodic oxidation surfaces like TaO2, develop TaO2 nanotubes and all those things on the surfaces, right? So all I'm saying is titanium is another material, biomedical material, and the way it's surface processed, there are many there are many methods, and they start from mechanical to biological surface preparation. That's right. So that's a takeaway. And current manufacturing methods. So these materials are currently manufactured by hot and forged method. Okay, you can actually think about how currently used biomaterials are processed. So they are processed by hot and forged method, and its surface is modified as mentioned, right? Once the hot and forged material is actually made as component, you can use any of these technologies to modify its surface, right? Uh, Then, as mentioned, so we can use sorting, acid etching, anodizing, or any other processes. And finally, you have a component like this. I don't know whether you've seen the biological biomedical implants. So those implants will look like this, right? It'll seem with a different color. Okay. So for example, so you're seeing here, the implant materials, different color. So those color then indicates that different types of oxides formed on the surface, right? For example, if I process the component with suitable oxidation, we call it anodic oxidation, that will give a different color. So based on the thickness and based on the nature of the oxide, it gives a different color. Okay, so finally, this component is what actually put into human body. Right? So all I'm saying here is the conventional processing is wrought and forged, and it is processed with once it is made. The surface is processed with either short peening, acid etching, and anodization, which we call the anodic oxidation. So that is suitable oxides are formed on the surface, so that they can actually fit into human body, right? So right, so now the same component, right? So now there's a good amount of research is taken place to process the same material by using a 3D metal printing process, right? So we call it's a laser powder, laser based powder bed fusion technique. We call it the LPPF technique. I believe most of you would have heard about this 3D printing. In 3D printing, there are various category or classifications. But as far as my talk is concerned, I will be restricting only with the LPPF. So wherein the raw material is powder, and we use a laser source to process the component, right? We use the raw powders, and CAD file will be prepared, and we just convert the CAD file into STL and make it readable by the machine. Then we actually print the component, right? So since it is processing layer by layer, so we have actually highly control at every layer processing, right? Like you are seeing on the right hand side. So once I prepare the component, so see every layer by layer, I have a control. So what I can control here is the energy, right, that I feed into the component. So there is one equation given here. So energy, which is volumetric energy, that is equal to so the power that I use over the scan speed over hatch distance over layer thickness. Okay, so I will be able to process the material. Okay, so now when I process the material, so this is what actually facility that we have at our institute. And yeah, so now, so this is a titanium processing. So now what you're seeing is it's a powder bed, right? So it has a very fine powders like sand. Okay, it is even finer than sand. So the laser is coming and interacting with the metal powder and selective impacting, and actually it's okay. So this is how the components are getting printed. So now, so the just a brief about how the processing takes place. As mentioned, CAD, and then convert that into STL file, slice, and generate G codes, right? So I'm not interested in getting into how 3D printing is working. So these are the components, right, which we process in our lab, right? You can see here there are various kind of critical components. Again, this justifies, right, why we use 3D printing, right? We should have proper justification why 3D printing is required to make a component. So there are some components listed here. You can see the first component which mimics exactly the bone structure. Okay, and there are some components which you cannot actually manufacture by any other conventional method. So that demands us to use the 3D printing process. Okay, so now these are some of the components processed with various materials, and whatever the bone-like structure that you are seeing, they all actually processed with the titanium material. Okay, now a brief like challenges involved in 3D printing. 3D printing or metal additive manufacturing is not the solution to make critical components. Of course, it complements the conventional processing. However, one has to understand the challenges involved in 3D printing. Okay, there are various challenges, but I just want to briefly mention the major challenges involved. One is, of course, porosity. Getting 100% porous-free component is challenging, but these days, so the technology is advanced such that so we can able to achieve very close to the theoretical density of the component. But however, so when we handle the process careless, we may end up with the porosity. Now, of course, spatter is there. Spatter, you just relate with the welding. So when you perform welding on any place, you can see there are actually some spatters. Similar kind of spattering is possible here. And as mentioned, because of layer by layer processing, it leads to large or huge amount of stress into the component, and sometimes the stress will reach the critical value that leads to the cracking. Okay, at the end. So you can see here that the components are cracked, right? While printing itself, right? You don't have to pull it. While printing itself, it will be cracking. So that's because of the internal stress developed. Okay. Now, of course, there are the staircase effect that lead to the porous component or porous structure. Could have seen. So, if you have noticed a 3D printed component, so normally it will have porous structure and a rough surface. And the rough surface we call because of the staircase effect. And very important, it's non-Euclidean microstructure, right? So, in the couple of slides before, I was talking about how these materials are processed conventionally, right? I mentioned art, roll, and forged, right? Conventional materials are processed by roll and forged, and it has a typical microstructure and phases, right? Those who are with mechanical and materials background will be able to appreciate what I'm talking about, the phases and microstructure. When we process the same material in 3D printing, we may lose actually. So we may end up with a different phase and microstructure, which is not desirable. Okay. So that's what we call it as a non-equilibrium microstructure. Okay. So we end up with a non-equilibrium microstructure, which will put the material in danger. Okay. Right. So then actually that requires processing or post processing. So these are like some, the powders that we use as mentioned. So we use very fine powders, and you can see the chemical compositions. And these are some of the components we processed, right? It's Ti64. And as I mentioned, you can see here the left bottom as-built image, right? The as-built image. So this is what we get. When you say as-built image, it is just the image that what you're seeing here, right? In the component printed, right? This is the product we made. So if I cut this component, and again, this is a 3D printed component, right? This is all the 3D printed component. If I cut this component and see its microstructure, that microstructure would like what you're seeing here, as-built. Okay, so this as-built microstructure is typically is having martensitic structure. It's called HCP martensitic structure, which is hard and kind of having less ductility. Okay, and these structures will have martensite. We call it as a alpha prime. Okay, so as built structure normally possesses alpha prime martensitic structure, which is the HCP martensite. But our conventional materials will not have alpha prime. That will have alpha and beta. Okay, that alpha is HCP structure and beta is a BCC structure. So then I'm not getting that. Then what I should do? So I'm getting the as-built alpha prime, which I don't want, but I'm getting it. So I'm getting it because of high cooling rate, right? Imagine inside the 3D printer, the component will undergo extremely high cooling rate. So the cooling rate is equal to 1 million per second. It's almost like a 10 to the power of 5 Kelvin per second. Okay, which is very high cooling rate, and that high cooling rate will lead to form a non-equilibrium microstructure, as you're seeing here in the as-built structure, right? Which is alpha prime martensite. So, which is of like not giving the desirable properties, or I cannot use this into the purpose I'm thinking for. So, then what is the remedy or mitigation is that I have to take it for the heat treatment. Okay, why heat treatment? I need to restore the desirable phases or the structures, right? So what I'll do, I'll just take the material and heat it to close to the beta reaction temperature, which is almost close to 955 degrees Celsius, and do furnace cooling, right? So here we kept at three different temperatures, which is very close to the beta reaction temperature, namely 750, 850, and 950 degrees Celsius, right? And you can see that as the temperature increases, and there is a nice split out, and can see that the alpha and beta is separating out. Okay, and the size of the lathe is also increased, and particularly the phase fraction of the beta is increased from 2 to 6 volume percentage with the increasing the annealing temperature, right? So it is seen as a 2% for the case of 750 degrees Celsius anneal temperature, and for 950 or 6 volume percentage. Okay, you can see that with the XRD plot. In the XRD plot again, right, as we increase the temperature, so you can see that alpha and beta is separating out, and we can see it's a distinct. Okay, so now we have also actually done and EBSD. So the structure that you are seeing here is the EBSD structure of aspirant and heat treated, and which shows there is aspirant structure is having legs kind of modern side, and it is completely absence of beta phases. With the increase or with heat treated samples at 850 degrees Celsius, so there is a beta phase, right? Of course, you can see that there is a phase fraction, so which you can see that. Are you able to see my cursor moving?
Yes, sir.
Fine. Okay, so you can see that with 850 degrees Celsius, so, you can see there are actually the beta fraction which has come out from the super saturated solid solution, and they are in the green, right? And this volume fraction is about 3% in this case, 850, and it increased to 6% in the case of 950 degrees Celsius, right? And no, so with further analysis, we also noticed that so there is uh, this alpha and beta that obeys the Fudger orientation relationship. Okay, and if you see, so with this we can make a conclusion that so the beta is coming out from the saturated solid solution as we increase the temperature. But however, we need to have further correlative microscopy to study further advanced what is happening at nano level, or even at a lesser scale, right? Say, for example, are there any segregations at the nano level, or are there any nanoscale features are present? Okay, and what we have done, we have taken this material into the further studies, and you can see that this is as printed and heat treated samples, and we did an APT analysis, right? In the APT analysis, there is a clear distinct that with as-built samples, whatever you are seeing, these are actually as-built sample, right? With the as-built sample, so there is segregation, right? You can see this all actually concentration profile. And you can see this are the elemental distribution, right? How titanium, aluminum, vanadium, and silicon is distributed. And you can interestingly note that. So there is a segregation curve, right? So this is called vanadium segregation. You can see that. So the scale is in nano, right? So imagine we are actually talking about nanoscale, right? The X distance here is in terms of nanometers. Okay, so and this is the elemental mapping is done at a very low nano level, and so we are taken at this right at nano level elemental mapping. You can see that there is a segregation. Okay, segregation is so that it's a kind of a clustering of particular atoms, and that's because of high cooling rate. Right, this is happening. So this is what you can see in the such cluster is taking place at a nano level. But no, we actually we need to look into this, how this clustering is changing with respect to heat treatment, right? But if you look at it in just generic EBSD structure, which includes of course a TKD and then a TEM structure, we don't see that, but we can see that with the APT structure, right? APT is atomic probe tomography, which is advanced level of microstructural characterization technique. Okay, right. So the takeaway is there is a segregation. Now, how that segregation, segregated component elements appears when there is a heat treatment. Okay, so upon heat treatment, and very important. So wherever there is a segregation, you can see it's all segregation. Wherever there is a segregation, right? There is nothing but there is a tendency for a defective formation, right? So there is a tendency of segregation of vanadium silicon towards the defective sites. So which means those regions so we'll be seeing with good amount of large amount of dislocations and grain boundaries because they are all the defects, right? So wherever there is a such segregation, defects will be concentrated. Okay, right. So these locations they will act as a potential nucleation site for beta phase during the decomposition. Okay, right. So upon heat treatment, so what happens? These all the regions where this beta phases started coming out. Say, for example, you can see here this is heat treated samples with some 50 degrees Celsius, and you can see these all some beta phases they are coming out, right? So these beta phases, right, actually they are coming out from those interfaces, right? Wherever we have seen there is a segregation. So those segregation regions are potential uh, site for the nucleation of the beta phase. Okay, and at a low temperature, the driving force is different. At high temperature, the driving force is different. Okay, right. So you can see this, right? So how the beta phase is actually coming, right? So and of course, right. So now with annealed, you can see there is a diffusion of vanadium that which controls the advancement of alpha plus beta interface. Right? So you can see that with a higher amount of heat treatment temperature, so there is a good amount of diffusion of vanadium that is taking place. So you can see there is a no, alpha plus clear alpha plus beta interface, right? And there is seen with even EBSD and TKD, right? There is a clear alpha plus beta interface is seen with that, right? So, so based on this, we propose actually. So how the microstructure is, our evolution of microstructure is taking place with respect to 3D printed titanium 6 aluminum 4 vanadium alloy. You can see that as built material, as a lot of segregations and dislocations, density is high. Upon heat treatment, those dislocations regions will act as a site for the nucleation of a beta, and beta is coming out from solid solution, and the size of the beta is increased. So, of course, and there is actually validated with elemental mapping as well. Okay, and these components we have taken for simple mechanical property studies. You can see this is simple tensile testing done as print sample. So is showing very high strength. The strength is almost 1,200 MPa, which is extremely high strength, and which is good. But you see the ductility is very low, right? So here the ductility is almost, it is about 8%, right? Very less ductility, which is not good for biomedical applications. Uh, any question?
No, sir. No, sir.
Fine. Stop me if I'm exceeding time, okay? So,
Yes, sir.
so now this is this material, the as built material, as printed material, is seen with very high strength. But the drawback is the ductility is very low. You see this blue curve, ductility is very low. So that actually will put us in concern or worry. So with the heat treatment, you can see that so the strength has decreased, and the ductility is regained, right? Which is good. So 1000 MPa is good amount of strength. Of course, there is a loss of strength. At the same time, there is a ductility is restored, right? Which is very good. Okay, and the ductility is restored, and because of the formation of beta phase, which is soft and ductile phase present in the titanium material. Okay, and this is a nice study we did, and it's a good understanding we got about processing of titanium material with 3D printing and how the as printed structure shows, and we could be able to relate that with respect to macrostructure, microstructure at atom structure level, and then we'll be able to get the understanding. Okay, you can see here. See, so with the increasing the temperature, you can see that so the amount of beta is increased. Okay, you can see there is a clear distinct. So we cannot actually keep increasing the temperature. There is optimum. You can see what happened further if you increase the temperature. So at 950 degrees Celsius, you see the strength has decreased considerably. And again, the ductility also decreases, right? So there is the optimum value. The optimum value is like 850. Okay. Are between 750 to 850, right? So maybe this 850 is what we found optimum temperature for
Sir,
heat.
I have a small question, sir.
Yes.
Sir, supposed to be the if we have heated again for a above 950 degrees centigrade, the whatever it is going to be changed, that alpha prime, it is going to be changed like that, sir.
Mhm.
Whether it will be changes the as built structure, that I am
Uh,
asking.
yeah. See, again, the aspect structure that depends on cooling rate. I think I have shown in. Sorry, I'm rushing my slide. I
Yes,
show here. See, uh, see, you can see here. No, this is the beta transition temperature. Okay.
yes, sir.
So what I should do, I have to actually take it to above beta transition temperature. Okay.
Yes.
If to beta transition temperature, of course, no, the size of the lathes or grains will be become extremely larger, and the grain coarsening effect will come into picture, and that will lead to other issues like we are saying. There is a sudden drop in ductility and strength as well. Okay, so we are playing the temperature very close to beta transition temperature. Okay, very close to beta transition temperature, which is like uh, close to like say beta transition is 955. So if we go 950, even the 950 is not actually working with us, right?
Oh,
If we lesser 850, it is working. If I keep decreasing it, what happens? I'll not be able to convert the alpha prime, which is HCP martensite, into alpha
mm,
betas. That will be issue, right? So I cannot go very close to the beta transition issue. At the same time, I cannot keep a very low temperature. Again, issue. The issue with the low temperature is I'll not be able to convert the as printed martensitic structure
sir,
with.
and additionally, it is not related to the same titanium. Suppose if I'm going for some other material, it is based on high temperature application materials. So the application itself going to be high temperature. Whether the structure will be follow the same procedure. Suppose if the exposure temperature is going to be 1,000 means, then the either incodal or some other material will be again will follow as-built structure, or how
Yeah,
we can respect it.
yeah, I got your question now. So, see, before we, taken to the heat treatment, one must understand or should know the bit about the physical metallurgy concepts of the material, right? So, what are the phases present in your material? And you must know about its TTT diagram or cooling curve phase diagram, right? What are the phases that you expect? So you quoted something like superalloy. Okay,
Yes.
so superalloy, so we call it a superalloy because of it. It has desirable strength at high temperature. Because of it has the some desired phases at high temperature. Okay, it's the gamma prime or carbides or some precipitates. Okay, to get those precipitates, then you must do suitable heat treatment. So it's a long, make it short. Is that
Okay.
one has to know about the phases present and about the cooling curve. So otherwise, we cannot actually plan this. Say for example, here I kept it 850 and furnace cooling. So this I decided based on because I know it's cooling curve or
Yes.
TP curve, right? So
Yes,
I'm
sir.
setting this based on that. So and I'm expecting, if I follow this temperature and time, I'll end up with this structure, right? So all I'm saying is one should have prior physical metallurgy knowledge on the material, so that
Okay.
right? Okay.
Exactly. Thank you, sir.
Okay, so so that's what actually here. So how the phase transformation is taking place, and this is the mechanism that we propose. So what is happening with low temperature and high temperature? So how the structure is getting split up? Okay, and we call it is boundary splitting, cylindrization, and edge spheroidization. So this is how actually what happens when I go to very high temperature, so sometimes I may actually end up with some termination. You can see here, right? So this kind of aspirated structure at at a very early stage will get split into like this, right? So I may even actually end up getting a completely like a circular structure, right? You can see, there are some cases with very high temperature. This will not possible at a low temperature. Only at a high temperature I will be able to see such structures. Okay, so this is how so we have to actually see, because choosing temperature, the materials are very sensitive to time and temperature. Okay, so if I choose wrong temperature and the wrong time, I may end up with completely different microstructure, and that will give completely different properties. So instead of actually making use it, I will end up killing the material, right? So that happens if you don't choose the time and temperature properly, right? So in this case, I would say that so I end up actually getting into some kind of globular structure, which were not there in the originally printed samples. Okay, right. So this is how we also propose the mechanisms, right? And how the boundary splitting is taking place with this material. Fine. So now these materials are used for various applications. In, as mentioned, THR is one of the applications. We call it the total hip replacement. You can see the total hip replacement. There are various materials used, right? You can have metal on polymer, metal on metal, ceramic on ceramic. There are various combinations available. But if you look at the cross section, right? I'm talking about this, acetabulum cup, right? So probably you would have heard about this acetabulum cup. If you look at the acetabulum cup, right? So it has different section. You can see here the top surface it will have very rough, and it has some solid, and depending upon the material, whether you have polymer inside or metal inside or ceramic inside. Okay, right. So this is how the acetabulum cup, and there are so various problems. The common problem is aseptic loosening is a common problem, and you can see there is an interface. So this is a bone and this is a stable cup. So you please understand this is a stable cup, right? And on top you have bone, okay, bone and a stapler cup, and there is an interface, okay, and there is an interface, and this will actually so this will actually this will experience some amount of compression, okay. So this is a stable cup, and so it will experience some compression bone and right, this is oxidic what we call it as. All right. So so now what we are doing in our please, we are actually making this component with the auxetic structure, right? Auxetic structure, as the first one, so far I talked about how we process the material. It is not just simply print and use it. As a researcher, we should not do that. We should understand what is its the structure property correlation, and we should also actually understand the defect, right? The mechanical properties. So that's what I talked about the earlier. So there's another area we work is metamaterials, right? Oxidic metamaterials. The bottom material that what you're seeing is the metamaterial. This metamaterials, it's nothing but kind of it is kind of a unit cell, right? In a simple, right? So conventional structure is what I talked about, and there are non-conventional structures. So in metamaterials, there are various classifications. Let me not get into all these things. Metamaterials, so lattice metamaterials, and its use and all those things. Maybe I'll skip considering the time. So there are various metamaterials. Okay. So it is plate based and TPMS based and stress based metamaterials. So and very important. Okay. So these metamaterials. Okay. It has to follow some stability criterion, right? So let me take the lattice metamaterial. Okay, so that's what now we mostly work on. The lattice metamaterials, for example, if we take very simple, lattice structure. Okay, so what happens when I press, it actually getting compressed. So it is called a bending dominated structure. Okay, so I cannot have structure like this. I press, so it gets stretched. Okay, it is stretching dominated, right? So it depends loading direction. Loading direction is parallel to the strut direction. In this case, that lead to stretching or compression dominated. The loading direction is inclined to the stress. This is what now we are seeing here. That leads to the bending. Okay, so stretch dominated, bending dominated. And that again depends on what is the Maxwell's stability criteria, right? So based on this Maxwell equation, you can actually find whether the component or lattice that you produce is stretching dominated or right. There are various applications, right? These are some of the lattice metamaterials. There are various applications. Okay, I'm restricting this with respect to biomedical. And you can see this in the biomedical as mentioned. Yeah. So, so here you can see, so when I compress it, what happens? So normally when the material is compressed, the cross-section area is increased. Okay, right? So that's a conventional structure. So when you use the oxidic structure, oxidic metamaterial, when you compress, what happens? So the cross-section area, instead of increasing, it will decrease. Okay, so we call that as a negative Poisson ratio material. Right? For example, you take here, no, right? So what happens when you compress, right? So it gives a negative Poisson ratio. Okay, and it has no very so a variety of applications. Okay, right. So so what we do? So we actually take this and we use this criteria, we call it as K, so singular stress field. Okay, so the singular stress field, it is a kind of essential to mention whether the designed component will give the singular stress field effect or not, right? So if it's a homogeneous body, this is what we use. This is nothing but a K is equal to stress times root pi A. The A refers to the crack, the size and the crack size, and the F is applied, load. Sorry, F here is the factor, right? The sigma is applied stress. So now, so we can actually design the component whether to have a singular stress or non-singular dominated interface. Again, this interface is with respect to the interface that is used in the biomedical applications. Okay. Again, this all is some of the equations, right? So this is to define the structure of a component, and we process this material and this is how actually it is processed, right? You can see this. The material is processed with two different components. One is with metamaterial, and the other one is with artificial bone material. And we take this and test it. We just apply the compression test, right? So what do we do? So here you can see that there is a the material that is getting compressed with the singular and non-singular component. You can see that the load deflection curve or the stress resisting curve is different, right? On the left hand side, you can see when you compress, bone is getting actually fractured. On the right hand side, when you compress, the bone is safe, right? So this is what the so-called I talked about singular or non-singular structure. So this is a metamaterial. Again, these metamaterials have 90% ratio, number one. And not only that, it also has a non-singular effect, right? So if we have a metamaterial with a non-singular effect, we use that in the bone, so your bone is safe, right? Whereas the component will lead into some fracture. Okay, right. So we have done actually further studies to see how the mean load looks with respect to singular and non-singular structure. And for a singular structure, the mean load is keep decreasing, which means it has more and more compressibility. Whereas in the non-singular, it almost remains flat, right? Which is good in case, or we know what is the limit of it. Okay, and we also actually seen how the interface looks, and the interface with singular, so there are actually cracks, right? At the interface, there are cracks in, whereas in non-singular, the size of the crack is minimized. Okay, so with that, so I can make a quick conclusion that the heat treatment as printed component is uh, as printed titanium materials are uh, giving high strength but less ductility. But this has to be heat treated. Okay. There are no other materials used in biomedical applications. And when there is a heat treatment, uh, the strength is compromised, but ductility is restored. Okay. Uh, and we also actually studied that at various scales. Okay, from macro to micro scales. Then we have actually we also actually started working on this toxic metamaterials, which right which is used to give it's used to actually take the good amount of load absorption, and keep the bone safe. Okay, right. So with this, let me close my talk. If any questions, I can take it.
Thank you, sir. Thank you for the wonderful talk, sir.
Yeah, sir.
Uh,
Yeah, ma'am. Please continue, ma'am. Please continue.
yeah, no, yeah. No, Mohan, sir, you can continue.
Thank you, ma'am. Yes, it is a wonderful session on implants. Actually, the session is very informative, and many of the participants put in the chat box. It is very interesting and more informative. Uh, okay, sir. Shall we go for a few questions, sir?
Yeah. Yes,
Uh,
yes.
yeah, please. Any participants have any questions? Kindly mention in the chat box. Raise your hand. Yes, shall we wait for a few questions? Before that, I have a few questions. Actually, you incorporated lattice structures into implants, right?
Yeah.
Yeah. Did you uh, incorporate any oxidic structures which have negative stiffness structures, uh, negative stiffness behavior in its. Did
Yes,
you
yes, yes,
tried anything?
yes, yes.
Yeah, in that during the compression, did you capture regain graph for that sustain curve for that?
We have not done that, as such in a component. We have done that with the sandwich structure, right? So, of course, we know that the structure that we design will give the negative Poisson ratio, and we know that, and we actually sandwich that with artificial bone material, then we compress it out. So, and we know that it will give the negative Poisson. So, I don't have any right results to show you how much negative Poisson ratio the value that you got, uh, but yes, it will give.
Yeah, actually, that is one of the another one research area that I hope, because I also done my research in lattice structures only. Many of the people doing only stress strain curve up to densification region. When we go with the axiatic like negative stiffness structure, we can work in the reverse order also. By take away the compressed load by step, we can get a negative stress strain curve of the that means replicate of the previous one. Also,
Yeah,
another
you're
one.
right. So, and most of the researchers, they I appreciate, they put a lot of effort in making the component. No, but no, so they actually process the component without understanding the metamaterials or oxidic structure, right? So,
Yes.
but they take it and they compress it. We know that if you take the unit cell and compress it, what kind of results we get, right?
Yeah.
So, we should not actually repeat doing that. We know that initially there will be densification and it will reach to some flat plateau, and so yeah. So the conventional metamaterials would look like this, but oxidic metamaterials, uh, it shows different value.
Yeah, sir. Another one doubt question. Actually, when we incorporated and using the implants with lattice structure or any other value addition, what are the medical related steps we need to do after fabrication with the powder bed fusion additive manufacturing process?
So, actually, no. So, maybe surgeon can actually give the right answer. I don't want to mislead here. So, but as far as I know, there is a set of actual procedure. Okay. I know how the implants are manufactured. So it is kind of a manufactured and prepared in clean room, something like
Oh.
10,000 around lakh clean room standards. And before they put into use, that's what I mentioned. The surface are actually taken care, which means the material has to be cleaned with acid. Acid cleaning is necessary. Once the acid cleaning is done, then they'll take it for oxidation, right? Anodic oxidation, which essentially to make titanium oxides, right, on the surface. Okay, I'm talking about only titanium material here. So once the titanium oxides are formed, and those oxides have very good properties with respect to bioactivity. So this once the AOI is done, anodic oxidation is done, then it is actually sealed or maybe further taken care maybe for protecting the body. So I don't have full or right answer. But I can only mention whatever I know with respect to manufacturing on this.
Oh, okay, sir. Yeah, we got few questions from the participant.
Yeah.
The first question is how this additive manufacturing in healthcare can be related to management perspective. It is a question.
How how the additive manufacturing in healthcare is related to
Management perspective.
management.
That means I think he is expecting from any marketing related like kind of management. Okay, sir.
Sorry, no,
Okay.
sorry, I'm not able to
Uh,
answer.
I request this participant to mail you, sir, regarding this question.
Actually, there was one more question
Yes,
before
sir.
from Tejas Chauhan.
Yeah.
Sir, if we use 3D print object in medial line, then what is the strength of object? Is it feasible?
Sorry, repeat question again.
If we use 3D object in a medial line, then what is the strength of object? It is feasible. Like that is the question.
Offset, I know, sorry, no, I'm not getting the question. So
Okay.
maybe no,
Then okay, again,
you
let
said,
me
you
call.
please you send, yeah, you can give
Yeah.
me idea. I'll just.
Yes, that will. Then Dr. Gobishwaran sir asked, have you done any surface modification on the titanium alloy printed sample?
Yes, we do surface modification. So we have, as mentioned, both mechanical and chemical and electrochemical processing setup in our lab. So yes, so the material should be taken care, treated for its surface modification. Yes, we have done that. So these components, what I talked about, they are processed with mechanical modification.
Okay, sir. Thank you for this.
One more question is there, sir. From Anisha. As we discussed, the challenges in 3D printing, does 4D printing will overcome this problem? Asking about 4D printing. Yeah.
No. So these are all actually material specific and process specific. These problems, so maybe the intents of the problem will be reduced, but it will be there, right? So the problem that what I talked about is something microstructure related problem, and I don't think that will be taken care with the 4D printing.
Okay, sir. Again, one more question came, sir. Surface modification on the titanium alloy printed sample by which method?
The surface modification, there are so many methods, right? The surface modification, so people go for coating, and people go for a treatment like nitriding, okay, plasma nitriding. So nitrated samples are used for implant applications. So there are several treatments. It is up to actually um, uh, the requirement, right? So there are various methods available, right? We call that is thermal process, thermochemical process, and mechanical process, as I mentioned, electrochemical process. There are various processes available.
Okay, sir.
Okay, sir. Actually, this is a wonderful session regarding medical implants. Also, we got many information regarding lattice structures and how it will impact on the implants for the medical devices. Okay, sir. Thank you so much for this wonderful session, sir. We hope in future also we will get more session like this from you, sir. We will get in touch with you. And if any further questions also, we will our participants will mail you. I hope more informative informations and other things will get from you, sir.
Okay,
Thank,
right.
thank you so much.
Thank you for the
Yeah.
invite, and I'll be happy to answer those questions and your email ID, right? You can
Sure,
post
sure.
my email ID
Yeah,
below,
please.
right? So I'll be happy to answer.
Yeah,
Right?
thank you.
Nice to see a message from Kajiravan. Hello, Kajiravan.
Thank you. Thank you, sir. Thank you, sir.
Yes. Yeah. Okay.
Thank you, sir. Thank you for the session, sir.
Okay,
Wonderful
madam.
session, sir.
Thank you, Preeti, madam, for the invite.
Thank you, sir. Thank you, sir.
Bye.
Yeah. Thank you, sir. Then, yeah. Dear participants, if you have any questions, kindly put in the comment box. We will ask to the experts. Also, Tagore, Ashit Tagore, I think you raise your hands. We saw your notification, but kindly put your queries in the chat box. We will ask to the experts. Okay, thank you. Then we move on to next session, right? Okay, okay, yeah. Uh, I hope I wish to welcome our next expert, Roger Narayanan. I am happy to introduce him for our participant for the FDP program second day, second session. He is distinguished professor in the Joint Department of Biomedical Engineering at the University of North Carolina and the North Carolina State University, USA. He is globally recognized researcher in biomedical materials and processing technologies with more than 350 publications and several book chapters to his credit. His work span the processing, characterization, and application of biomedical materials for healthcare applications. He also serves on the editorial board of several reputed international journals and is an associate editor of Applied Physics and also reviews published by AIP. With extensive academic and research experience, he brings deep insight into transnational biomedical engineering. With this wonderful experience, today he going to give a wonderful session on 3D printing for medical devices. With this short note, I wish to hand over this session to our expert. Hi, sir.
Go ahead and begin. Give me a second here.
Yeah, sir. Yes, sir. We will start the session, sir.
Talk to 3D printing for medical devices. I'm Roger Narayan, professor at the Joint Department of Biomedical Engineering between the University of North Carolina and North Carolina State University. So I want to show some overall slides that describe a little bit about where medical 3D printing sits and overall technologies, and then I can discuss some of my work. So if you look at how 3D printing can be made into medical devices, you can see here how 3D printing fits into the value chain. Essentially, you have 3D printers being able to be used within a company or be outsourced. This is only after you have research and development, materials, and product design enter the picture, and you end up with a 3D printed medical device that then undergoes post-processing and then commercialization. There are many standards that relate to 3D printed medical devices. Here you can see standards that come from joint effort of ISO, the International Organization of Standards, and ASTM International. So you can see these are all joint standards between ASTM and ISO. And that's been going on for a decade now, that they have combined standards for this. And you can see they relate to general principles, material extrusion-based additive manufacturing, powder bed fusion-based additive manufacturing, later laser-based powder bed fusion additive manufacturing standards, data processing, environmental health and safety related to materials extrusion-based printing, the finished material properties for materials created by powder bed fusion, and then medical image data. So there's many standards here now. There are also ASTM specific standards related to metals, specifically around titanium, 6% aluminum, 4% vanadium alloy created by powder bed fusion. Also, there's one for the extra low interstitial standard for TI, aluminum 6%, 4% vanadium alloy. In addition, you can see here there's even one for nickel alloy with powder bed fusion. So many different standards can be used to understand and to keep the process parameters within a basis that is consistent with medical use. You can see here also country-specific or region-specific regulations. So you can see here in the United States, you have the Federal Drug Administration, Food and Drug Administration. In the European Union, you can see here many different regulations. And then in the Asia Pacific region, you have different health authorities, Australia, and all the large countries of Southeast, and East Asia. So when you look, you can see many different opportunities that are available for 3D printing. But you do see constraints related to regulatory challenges. And you sort of saw the regulatory issues that each of these countries has one or more directives that guide 3D printing. But there's opportunity around various technologies, either for creating an implant or for creating artificial tissues. When you look at patents, as you can see here, have applications have are in steady levels in the thousands. There are thousands of patents every year granted around 3D printing of medical devices. You look at recent patents, you can see here recent patents from 2023 and 2024 relate to inks for 3D printing, installation of a 3D printed device for 3D printing, of medical applications. You can see here also examples of trying to create fluorescent medical devices, creating a nitric oxide releasing material for 3D printing, 3D printing technologies where you can print based on an image, and then also delivering non-steroidal drugs through 3D printing. So when you look at sort of the market segmentation, you can break it down by 3D printing technologies, 3D printing materials, the actual way in which 3D printing is undertaken, so the way in which materials join together in a layer by layer additive manufacturing approach to create a 3D printed part. You can look at it by the way in which it's distributed by the hospitals or the universities. And you can also look at it by the application. So you can have a look at prosthetics application space, surgical instruments application space, anatomical model application space, and so on and so forth. When you look at the global market, you can see the global market for this technology has grown quite steadily over time until 2026, and then it's expected to grow quite a bit in the future years for software, for the 3D printing devices, and for the materials. When you look at the share of the market, the business share of the market for 3D printing of medical devices. The software and services are about a quarter of that, and the hardware and consumables are 3/4 of that. When you look at the consumables and hardware, and you look at that broken down further, about 2/3 of that is for the printers themselves, and 1/3 is for the input materials. When you look at the classes of materials, metals, ceramics, polymers, and composites, and others that are being used, you can see that polymer additive manufacturing, polymer 3D printing is the largest share, followed by metals, then ceramics. But you can see ceramics have grown quite a bit actually. So ceramics is a very interesting space. But you can see altogether quite a large amount of money. This is in billions of dollars, $1 billion will be going for hardware and consumables related to 3D printing for medical devices in particular in 2029. When you look at this broken down, you can see this in a pie chart that polymers are about half of the market, followed by metals, 1/3 of the market, and then ceramics and composites and other classes of materials being smaller shares of the market. When you look at the various approaches for 3D printing, one of the things we see is that vat polymerization or stereolithography is the most common approach, followed by powder bed fusion, materials extrusion, then materials jetting, followed by binder jetting, and because of the expense associated with this technology, directed energy deposition is the smallest share of the market. You can see this in a graphical manner here, where you can see that vat polymerization is about 1/3 of the overall approach for 3D printing and medical applications, followed by powder bed fusion being 1/4 of the market, and then materials extrusion following closely after that, with the other classes of processing approaches being much smaller shares. In terms of the customer or the distribution channel can be used for distributing 3D printed medical products. As you can see, direct sales is actually quite a bit of the total. So direct sales include direct sales to hospitals, universities, and then the other part of the global market is the medical device manufacturers themselves. And that's of course much larger because obviously they're purchasing these components to use them in-house for processing. But you can see here that by 2029, the market will be $4 billion US. When you look at this in a graphical form, you can see quite markedly that the medical device manufacturers are the big consumers of technology and supplies and materials, capital equipment related to 3D printing, and direct sales is a smaller portion, being around 15% of that market. When you look at the sort of end user from direct sales, you can see hospitals, universities, and others take up that side of the direct sales component. Saw the direct sales listed here. So you can see this is a certain proportion of the market, but the biggest component is this medical device manufacturer. So medical device manufacturer is 83%, direct sales 16%. Of that 16%, as you can see here, is broken down between hospitals, universities, and others. When you look at the global market for 3D printing of medical devices, as you can see, the largest portion is dental, and many types of dental products are now made by 3D printing. So you'll see, I think, almost the entire workflow for dental implants, dental appliances, and other dental products move to 3D printing over the coming decade if it hasn't already happened. And you can actually see that this is now a very large market in itself, over $1.5 billion. Then we see prosthetics and orthotics being a large fraction of the market, followed by surgical instruments, anatomical models, medical implants. And so you can see how dental products are a significant proportion of this overall 3D printing market. When you look at it in a pie chart form, you can see this where dental is about 40% of the overall medical devices market. You can see here now that medical prostheses are about 1/5 of the market, followed by uh, surgical guides being about 1/6 of the market, anatomical models being about 1/8 of the market, and then medical implants themselves, which we think of as being a very high technology area, being only 3.6% of the market. So this is a sort of very eye-opening slide indicating that, in fact, most of the resources in the 3D printing of medical space are being devoted to dental products, dental implants, dental appliances, with prosthetics and orthotics being smaller number than surgical instruments and guides, followed by anatomical models and medical implants. When you look at the sort of worldwide distribution, we see that the largest growth of this market is in the Asia Pacific region, being the largest percentile growth. But the largest, and this will be actually the largest overall number as well in 2029. So if you look at China, Japan, Korea, South Korea, Taiwan, Vietnam, India, all of these countries, I think, will have significant growth in the 3D printing medical market to be the world's largest region. You can see that's much higher numbers than North America or Europe. So this indicates you'll have significant growth in this Asia Pacific region over the coming years. When you look at North America, you will see here, of course, is dominated by the United States, and that's continue to grow at 12%. But as you can see here, actually the growth in Asia Pacific will actually be a little bit higher than that. When you look at the companies that are involved in 3D printing medical devices, it includes, as you can see here, it's a global expertise, including Hewlett Packard, which is now a Dutch company, 3D Systems, which is a US company, EOS, which is a German company, Stratasys, which is a Japanese company, and Materialize, which used to be a Belgian company but is now a US company. So that's sort of the market description, and you can see this is all from a global market report about 3D printing of medical devices. So that's sort of the introduction to this topic. Now I'll get into sort of a description of the technologies in general, and then I'll get into a description of my own research in this space. So when we look at scaffold fabrication, of course, these are typically performed by subtraction or removal of materials, conventional subtractive sheeting processes, or casting or molding processes. And so we see that most of these technologies are not suitable for tissue engineering or other medical applications. They often have forms of imperfection that restrict their use. In many cases, they involve the use of toxic solvents that could lead to residual solvents being retained in the device, and porogens that are entrapped inside a polymer matrix. So we also have challenges related to dependence on manual skills, experiences, and procedures, poor reproducibility and poor consistency of final product, high labor involvement, long processing times, poor flexibility to produce complex structures, and limited control over the internal structure of the final part. So people started creating these efforts that were originally called rapid prototyping, then additive manufacturing, then 3D printing. So you can see here, dates back to Charles Hull, who in 1988 demonstrated a stereolithography apparatus, which is involved the, the basic fundamental concept of 3D printing, which is layer by layer additive processing to create a three-dimensional part. This involves the use of surface digitizers or 3D medical imaging systems to generate patient data. Then this data is sliced into thin sections by computer. This data taken from the computer and it moved to the rapid prototyping machine, or now we call the 3D printer, creates the part in a layer by layer manner. And so these layers represent the cross-sectional data of the computer-generated slices. The materials are then stacked together and fused in order to create the three-dimensional part. In this way, the first layer of the part has a geometry that's defined by the first cross-sectional plane that's generated by the computer. This is bonded to the starting base. Then you have additional layers bonded on top of the original starting point based on their cross-sectional planes. And this process is repeated until the structure is complete. There's a lot of effort to take parts from 3D printing and then use them as the basis for molding or to create replicas. This is called indirect rapid prototyping. And this is the idea that you can essentially take a low melting point material and then you can then perform casting in order to create replicas of a 3D printed part. So indirect rapid prototyping involves creation of replicas, and the alternative is direct rapid prototyping, where you're taking the usable part that's created by we originally called rapid prototyping, then called additive manufacturing, and now called 3D printing. And direct rapid prototyping is basically using the part that directly comes from the machine as the usable part. So it's important to realize that there are two of these options that are available: directly using the part from the machine, and then being limited by the type of material and the characteristics of the material that's used in the printing process, versus indirect rapid prototyping, where you can move to many different classes of material that are all consistent with a molding or casting approach. So we saw an original chart in the first slide of this showing how additive manufacturing or 3D printing fits within the original sort of scope of medical device manufacturing, medical device distribution. Now we have another flow chart here showing how patient data can be inputted into the 3D printing approach. So you can see your patient data entering for the system for 3D printing, then be used to produce a part that then could be used in surgery. So you can see here examples of this approach, where in fact you're taking medical data and you're transferring it, slicing it into individual slices, and then you're using that data to then create a 3D printed part. You can see here how, in fact, when this data is converted to slices, it can then be used to create, for example, this part that could help surgeons reconstruct damaged tissue on the head. Of course, one of the earliest and most common uses of 3D printing to this day is in surgical planning, especially for complex surgeries. So you can see here, this is a study from 1998 showing how individuals who had anatomical anomaly who had that data captured by medical imaging, and then a 3D printed part was created to understand the defect, and then this was used to help the neurosurgeon plan their experiment. Here you can see someone with squamous cell carcinoma of the nose, leading to when that cancer was resected, this large defect. And then you can see here, this is how you can make a prosthetic that can then fit over that defect, allow this individual to sort of have a fitting prosthesis over the side of the defect. There have been many studies similar to this. This is one of the earliest ones where you observe a defect that in this case apparently was created by trauma, some sort of trauma to the skull, leading to damage to these bones. Then you end up having a CAD model being made of the sort of damaged bony tissue. You then can use this structure made by stereolithography. So this is stereolithography of a polymer. It was then used as the basis for investment casting. So then you use this as the basis for titanium casting. And then you can create a titanium part that fits over the skull in that way manner. So there are many advantages to this approach. You can verify the design. You can verify the design for manufacturability. You can assess maintainability, assess the reliability, assess the structure via visualization. You can print small volumes of the material. You can have design changes. You can do process planning like the neurosurgery process planning you described earlier. You can also do technologies where you have either rapid tooling or no tooling to create usable parts. The advantages of this is that you have the ability to create structures that are spatially and anatomically accurate with complex interior geometries. The disadvantage is that many of these systems are optimized for producing high dense prototypes and are limited in terms of their ability to create porous structures. So one of the things that people are now looking at and have looked at for the past 1 or 2 decades is the idea of creating porous structures that have interconnected pore networks. The idea behind the interconnected pore networks is that it allows for the ingrowth of cells, to provide a mechanism for uninhibited diffusion of nutrients, gas, and waste to have allow cells that have entered the scaffold to have undergo metabolism to provide energy and excrete waste. In addition, you need to have appropriate mechanical strength for a porous structure to allow for the structure to remain intact after implantation. So, of course, we see a lot of efforts to try to tissue engineering, and tissue engineering has made significant progress, especially around something like the skin. So the skin has been the area where tissue engineering has exhibited sort of translation and is now sort of a gold standard technology, whereas in most other areas, tissue engineering remains a laboratory study. We see even to this day, and now for several decades, the idea of taking the patient's own cells and using them as the basis for creating hybrid structures that contain a scaffold and the patient's own cells in order to create a structure that will eventually sort of retain those features of normal skin. Other things that one has to look at when performing 3D printing is to have good biocompatibility, non-mutagenicity, non-antigenicity, non-carcinogenicity, non-toxicity, non-teratogenicity, good mechanical strength, appropriate surface structure, and appropriate degradation kinetics. So people look at all different classes of materials, including ceramics like hydroxyapatite, tricalcium phosphate, and other forms of calcium phosphate, polymers such as polyglycolic acid, polylactic acid, and others, as well as natural materials like collagen, chitosan, and fibrin. These techniques can be separated into solid-based techniques, like lamination of solid sheets in order to create a solid structure, powder bed fusion, which is where you end up having aggregation and solidification of powders that are distributed on a surface in the shape of the final part. Fusion of the powder creates a structure that is in the design of the original 3D printed, the 3D design. And then liquid-based techniques such as sterilization apparatus, where you're taking a liquid precursor, such as a polymer that can undergo photopolymerization, and then have it selectively polymerized with light from a laser or a lamp in order to create a solid polymer structure. So when you look at all of these 3D printing techniques, one of the things that you see is that, first of all, this slide is 18 years old, but it still remains correct to this day. That in fact, all these techniques that we're using even now for 3D printing of medical devices are still limited by the same challenges that were identified at the beginning of my career 20 years ago, in that these are all very much limited by resolution, with 2-photon polymerization being the smallest resolution with features below 1 micrometer. Stereolithography apparatus now can get down to 5 micrometers, and then selective laser sintering can make much larger parts, much larger features. All of these other techniques are also, as we'll see, involved with creating larger scale features. You can see the strengths and the weaknesses of each of these techniques listed here. So in terms of solid-based techniques, you have the idea of taking a solid-based material like a filament, a wire, or a pellet, and then fusing it in order to create a final part. So the sort of first and most common approach that has been described is Stratasys, the approach called fused deposition modeling. This is an approach based on use of a filament as a precursor, extrusion of this filament, which is a hot filament, and then having essentially that filament cool in place to create a final solidified part. And you can do this filament-based printing with polymers, you can do it with other types of materials that include some ceramic-containing components. In this case, the material is extruded from the nozzle in the form of a thin filament. You then print this material basically as you would sort of deposit a tar to make a road, sort of pattern material roads onto the surface, and then you use an elevator platform to control the Z direction, the height, and you move the nozzle that's depositing the material in the X and Y direction. So similar to a glue gun, you heat the material, then extrude it, you create this filament that's extruded, and it deposits this material onto the surface, and the material attaches to the material underneath it on the previously deposited layer, solidifies, you create a layer of the material, you then lower the platform with that Z direction component of the 3D printer. You again move the nozzle in the X and Y directions to print another row of the material. These rows are typically arranged in a parallel manner with predefined spacing. The spacing is called the raster gap spacing. And what we see is that variations in the angular direction of material deposition for each individual layer can be used to create scaffolds with honeycomb-like microarchitectures. This is an example of the approach where you have fused deposition modeling, extrusion head, liquefy the material, print the filament. They're creating these various rows. They're spaced, defined with a part, and then you end up creating a final structure. This approach is relatively inexpensive for creation of models. There's no exposure to toxic chemicals, lasers, or a liquid chemical bath. This is limited in many cases to materials with low melting points and low melt viscosities. In addition, you have to convert the material, which usually doesn't come in the final usable form. You have to convert a material that comes in the raw form, call it powder or flake form, into a filament form. A variation of this is the bioplotter. Bioplotter is where you have an 80 micrometer needle. This large microneedle bore allows for printing of a variety of different components. Essentially, this works in the same manner as fused deposition modeling. You print the material in X and Y directions with this needle, and then once the material leaves the needle, it's then processed and solidified by cooling, heating, or chemical reaction processes. This technology is compatible with thermoplastic polymers, hydrogels, collagen, fibrin, and a wide variety of biomaterials. Here you can see an example of the bioplotter being used to create this honeycomb-like structure. In this case, the printer is a syringe printing material that's solidified once it reaches the surface. You also have low deposition modeling, which is where you freeze the liquid precursor. This frozen pattern is then freeze dried, which preserves the pattern. The advantage of this is that if you have a biological material like a collagen or a chitosan, another class of material, you can in fact sort of take advantage of the thermal properties of that material to choose an optimal processing and storage temperature. So as you may know, collagen is one of these materials that can be used in many different medical applications, and low deposition modeling or low deposition manufacturing can be particularly important for manipulation of freeze-dried collagen structures. So in fact, here you can see this, in particular with collagen being used, and you can basically process the collagen, freeze dry it by basically having the liquid collagen being used with nozzle-based printing on a frozen scaffold. And you have a freeze drying technique being used as the post processing so that you retain the structure and the properties of the collagen. So this is, as you can see, a two-step process where you start out printing with a frozen scaffold platform, and then the material undergoes freeze drying. Another option is powder bed fusion. So this can involve metals, polymers, or ceramics. This is where you are essentially using a liquid binder to help create a fusion of powder in order to create a defined structure for each layer of the material. You can, in many of these cases, you're using a binder to join together the material. You then have a roller, put a new material, better base of material on top to build the subsequent layer. You then also use heating of the structure to increase the bond strength to help these powder components better join together. And if you are performing appropriate sort of powder bonding approaches, you can oftentimes get high strength of the processed material. If you choose the appropriate powder dimensions, processing parameters, and heating parameters, you can get strengths that resemble those of the sort of base material. One of the things that you also need to worry about is when you're binding together materials, the binding agent can be a concern. If you're binding together, in this case, a polymer powder with chloroform, the chloroform binding agent can be a concern. You can use liquid carbon dioxide to remove that solvent. Here you can see hydroxyapatite implants before and after implantation created by powder bed fusion. And you can see the advantage of this is that you can print a structure that doesn't require very much trimming, and you can essentially use the part coming off of the printer directly in implantation studies. Another approach that's commonly used in implant processing to this day is selective laser sintering, where you're sintering together powder material. Powders are preheated close to the melting temperature. You then are using a carbon dioxide laser to create a further rise in temperature beyond the melting point so that you have the powders joined together. You then add subsequent layers of powder. You then do subsequent laser processing steps, and you can build together a metal part in a layer by layer manner. You can do this with metals, you can do this with polymers, you can do this with polymer coated ceramics, many classes of materials. So you can see here examples in the biomedical space, well, in PMMA coated calcium phosphate powders, but also polyether ether ketone, which is a very difficult material to process otherwise. Of course, this is a high temperature polymer, so the ability to process this with powder bed fusion provides great benefits. Also, you can process polylactic acid and polycapryl-lactone. Here you can see some of the advantages and disadvantages. The advantage is that you can easily create visual representation models. The parts don't require post-curing. You can get layers that are down to 75 micrometers in thickness. The disadvantage is that you can oftentimes, if you have certain features like sloping features, you'll see stepped artifacts. So basically like a stepped staircase sort of morphology, because the layer thickness is 75 micrometers and you will easily recognize the artifact layer by layer printing in a selective laser sintered part from the fact that the layer thickness is in a double-digit micrometer regime. You also have to think about the pores. There are pores that can be generated by this process that are dependent on the particle size of the powder. You oftentimes will have powder, these pores distributed over a wide range of values. In addition, this approach can involve high processing temperatures. So here you can see some details on the human osteoblasts grown on polyether ether ketone peak with 1% carbon black, peak with 10% tricalcium phosphate and 1% carbon black. And you can actually see a little bit on how these structures can be used for osteoblast growth studies, bone cell-like growth studies, and essentially you can see that you do have good coverage. Although it should be noted that peak itself is somewhat sort of hydrophobic, um, and you end up getting uh, the advantage of uh, being able to add tricalcium phosphate to enhance cell attachment. But you can see there's really no difference here whether tricalcium phosphate or carbon black was added. Getting good cell growth on any of these, even though you would think on first principles adding calcium and phosphorus on the material surface would enhance osteoblast attachment and growth. You can see here the actual research result shows no difference the attached the addition of tricalcium phosphate or carbon black. You can see here examples of ultra high molecular weight polyethylene powder being used, and you can see here that in fact this is a challenge because you're having laser CO2 laser interaction with the material that can cause degradation of the polyethylene. You have chain scission, cross-linking, and oxidation. Porous nature of the precursor polyethylene powder imparts microporosity to the scaffold, which can be a benefit, but at the same time, you can have difficulty in terms of creating sheets of the material because of material shrinkage. Here you can see selective laser melting of titanium, 6% aluminum, 4% vanadium powder. This selective laser melting process overcomes limitations associated with powder-based processes. You can create nearly 100% densities and metallurgical bonding between surfaces. So that sort of is an overview of 3D printing techniques. Now I'll get into some of the work from my lab for the next 15 minutes or 40 minutes. So one of the techniques that we have in my lab is a technique that's called matrix assisted pulse laser evaporation direct write, or it's also called laser induced forward transfer. You have a UV excimer laser that transfers material from a cell coated quartz ribbon onto an underlying surface. You can see here, this is being used with calcium phosphate. Transfer, this is the ribbon. This is where the material is detached from the ribbon by the excimer laser. You can see here the parts that are transferred. So this image on the left is the ribbon. This is the cell quarter. In this case, it's not coated with cells, coated with hydroxyapatite. And you can see here the regions where the excimer laser has moved the material onto the surface. Here you can see the processed structures. Here you can see the X-ray diffraction pattern showing that the processed material retains all of the crystalline structure of the input material. So you see here that it's a highly crystalline material that doesn't undergo any type of amorphization. Here you can see an example where both osteoblast-like cells, MG63 cells, and hydroxyapatite are spin coated onto a ribbon. Then the laser has interacted with the ribbon to remove certain portions of this ribbon onto another surface. And here you can see the transferred cells, the osteoblast-like cells, the hydroxyapatite, and so forth. Over time, this has taken 72 hours after the transfer. You can see here that you have a high number of living cells and very few dead cells. You look at the transfer, the viability of the transferred cells. If you perform this at relatively low laser energies, called very low laser fluence values, you can get a high number of cells similar to cells grown on polystyrene. One thing that we've done is to try to use polymers to reduce the amount of energy imparted to the cells during the transfer process. It's being done with a triazine coated ribbon. So this triazine polymer essentially is able to have a reaction that absorbs laser fluids and does not, by having this as an intermediary layer, it essentially protects the cells from directly interacting with the laser energy. And so by having this triazine coated ribbon, you can reduce the energy needed for laser transfer down to 0.07 joules per centimeter squared versus energy of 0.15 joules per centimeter squared that would be required otherwise. Here you can see that the boundaries of the cells, the pattern cell regions are well defined. You can see here high numbers of living cells in the pattern regions. Here you can see examples of B35 neuroblast-like cells transferred. These are all B35 neuroblast-like cells, I should say. So these are B35 neuroblast-like cells at 6 hours after transfer. You don't see very many connections between the cells, but then you can see higher amount of cell density with longer axonal extensions at 48 hours. Here you can see, again, some examples of transferred cells, and you can see at 24 hours, the development of the axons aren't clearly observed, but at 48 hours on the right, and you have much more well-developed axonal extensions. This is the 24 hours on the left and 48 hours on the right. Here you can see another way in which excimer lasers can be used. So with this 3D printing technique, you can transfer material to the surface. You can also use the same laser for machining into the surface and creating channels in the surface. So you can create this three-dimensional structure. So in this case, we'll see the example of machining, where in fact you can see the example of 600 to 400. This should be a micrometer channels created through this laser machining process. And then we used much higher energies. You can see here 0.09 to 1.0 microjoules were used. And so then we had a box at the end, and then we were able to then pipette material into that box and then start filling these structures with cells, myoblasts, neuroblasts, human epithelial cells. So you can see your example of channels, 60, 80, 150 micrometers. Okay. Here you can see some examples of the channels, different channel widths created through changes to the laser energy density. And in fact, you can see here as you change the laser energy density, have these sort of significantly, significant changes in width and depth of the channel. So you can see in here that it generally doesn't show a significant increase in the width of the cut, 1 to 2 joules per centimeter squared, but then there's this non-linear increase at 2.2 joules per centimeter squared that may be due to other types of material degradation processes. So you can see here, again, example where you change the aperture size. By changing the aperture size, you can change the dimensions of the channel. Here you can see examples of cells grown in the surface. As we mentioned, we put cells in a channel, in a reservoir, and then flow them into these laser cut channels. And you can see here that you have good cell coverage. These are myoblasts-like cells. You can see here that they will align and form parallel features from 60 to 150 micrometers in width. And you can see here epithelial-like cells, 431 cells, able to also sort of proliferate within these channels. And so eventually you can get these structures that are sort of cell-seated channels. This is an interesting example where you have B35 neuroblast-like cells that will align within these channels. And then eventually these bundles will break free from the channels. They'll have enough cell quantity that they'll actually sort of detach from the channels that they were originally in. And then you have these delaminated neuron bundles that will come off from the micromachine channels. And you can see here examples of these delaminated channels. You can see here another example of micromachining, where you take electrospinning of polylactic acid and perform laser ablation in order to increase the porosity of these scaffolds. And so here you can see examples of these pores cut with the laser process. Then what happened is you end up using, as you can see here, a type 1 collagen gel being used to attach these laser blade scaffolds to each other to make like a sandwich, a multi-layered sandwich of these porous polylactic acid scaffolds. And so this product is the sandwich of many of these joined together with a type 1 collagen gel. And so you can then create structures up to 3 millimeters that are quite thick based on sort of joining together these porous polylactic acid scaffolds. Here you can see a high number of living cells, very few dead cells, or these adipose-derived stem cells that are grown in these scaffolds. Here you can see that the adipose-derived stem cells were able to proliferate on all of the assembled structures. You have a much higher amount of DNA within these porous scaffolds than within the non-porous scaffolds. You can also see much higher amounts of mineralized calcium within these porous scaffolds, which is when you are growing these adipose-derived stem cells in osteogenic differentiating. So you're trying to push these adipose-derived stem cells to behave like bone-forming cells. And so you can see here, when you do that, you're getting high amounts of mineralized calcium, these porous scaffolds versus the non-porous scaffolds. You can see that there's a good amount of adipose-derived stem cells that have seeded these porous scaffolds and have essentially on high level proliferation within these scaffolds. We've also looked at inkjet printing, which is similar to the inkjet printing you see in sort of consumer products. You essentially have a piezoelectric chip, a lead zirconate titanate chip that is then actuated and undergoes vibration. It's actuated. This sort of causes the ejection of a droplet in a controlled manner. We've done many studies involving this system. This is one study involving muscle adhesive protein. Muscle adhesive protein is a protein of the blue muscle that is grown in the Chesapeake Bay region of North America. These muscles attach to undersea structures like piers and ships and docks using L-DOPA residues. So you can see L-DOPA residues being a high fraction of the overall proteins within muscle adhesive protein. These materials undergo metal-mediated catechol complexation process. They can form hydrogen bonds also in order to increase the bonding. Orthoquinone groups also enhance cross-linking and adhesion properties of these materials. So we essentially inkjet printed muscle adhesive protein from the blue muscle, then applied iron chloride to increase the cross-linking. And you can see here details on the jet printing of this material. By changing the voltage, you will change the velocity of the drop material. You can create these patterns of material. And then you can see here examples where you can have minimal protein precipitation or cross-linking in the as deposited muscle adhesion protein, and as you increase larger amounts of iron that's deposited on the muscle adhesive protein surface, you're getting larger and larger degrees of cross-linking until you end up having this bulk precipitation into isolated networks of protein because there's excess iron. And so you can see here as you go from 1 to 1 to 1 to 10 to 1 to 100 levels of blood protein to the iron chloride, doing from 1 to 1 to 1 to 10 to 1 to 100. You're increasing the cross-linking, and then you have these isolated networks when you have excess iron. You can see here correspondingly increase in adhesion strength up to the 1 to 10 ratio, and then a decrease in adhesion strength at a higher ratio. You can see that you have strength of adhesion that also is quite uh, high for these systems, but not nearly as high as for conventional uh, acrylate-based adhesives. Now we'll come to stereolithography. Stereolithography is an approach where you're, as we talked about earlier, came from Charles Hull. Charles Hull created this approach in 1988. First additive manufacturing approach that involves selective solidification of a liquid resin. You then have an elevator move the materials that you're processing, uh, uh, converting the liquid precursor to a solid in a layer by layer manner. And you can use either a laser or a lamp in order to polymerize the material. So you can now see here some of the work we've done in stereolithography. Our typical work involving stereolithography involves creating microneedles for transdermal drug delivery and transdermal sensing. So you can see here, this is an example from 2011, where our first example of a microneedle created through traditional stereolithography. It's a solid microneedle that can penetrate porcine skin. You can then see here an example of where this an array of hollow microneedles attached to a conventionally built constructor can be used to penetrate pig skin and deliver a drug to the pig. Here you can see the metabolism of the radioactive isotope. This is radio-labeled glucose. You can see them here, the metabolism of the radio-labeled glucose that is evident in the sort of time points after that radio-labeled glucose was delivered with that 3D printed microneedle. We've also created a variety of different structures where we integrate microneedles for the biosensors. So you can see here a carbon fiber electrode that's spaced into the bores of 3D printed microneedles created through stereolithography. We then use a metal epoxy on the back to connect these carbon fibers so that we can create a working electrode for 3D electrochemical sensing. And so you can see here examples where we actually have these carbon fiber tufts that are placed at various points in the backing of the microneedle array. You can see here with the MTT assay, have a high number of living cells, relatively few dead cells when you use this 3D printing material, which we call eShell 200. Here you can see good microneedle to microneedle uniformity, height of the microneedle for about 1 millimeter, bore diameters of 375 micrometers. Here you can see the porcine skin, and you can see that apply the microneedles to the porcine skin. You can transfer trypan blue dye, and this images indicate that the microneedles remain intact after skin insertion. Here you can see some details on where you're seeing the carbon fibers within the bore, these hollow microneedles. The carbon fiber electrodes do not extend beyond the tip of the microneedle bore. Here you can see this idea of using this sort of device for hydrogen peroxide sensing. Of course, hydrogen peroxide can be coupled with a variety of different enzymes so that you can detect biological molecules. And here you can see that you are able to get these sort of characteristic CD scans for concentrations of 0, 50, 100, 300, and 500 micromolar hydrogen peroxide. So we have a linear range for the output 100 and 500 micromolar levels. We've also done this sort of study with carbon paste electrodes. Carbon paste electrodes have the benefit of low background current, low cost, the ability to renew the surface, and the ability to modify a carbon paste electrode with enzymes to improve functionality. So you can see here some details. This is essentially a rhodium that's modified carbon paste, and the enzyme lactate oxidase that's also modifying the carbon paste. This is then vortexed, homogenized, packed into the pores of these of this carbon paste that's modified with rhodium and lactate oxidase. It is packed within the pores of these 3D printed microneedles. Here you can see examples of the microneedles packed with the carbon paste electrode. And here you can see that you can detect lactate of physiologic range with this sort of electrode. Here you can see the detection of lactate in the presence of interfering molecules like ascorbic acid, uric acid, and acetaminophen. And you can see here that you have a negligible effect on the response of lactate. Here you can see good stability of the biosensor. So you can see here a stable current, a slight increase in the current over 2-hour time course. You can also see here examples of multiplex sensing. So in this case, you can see here the detection of glucose, lactate, and pH with a single microneedle array. And so this is again using a rhodium doped carbon paste electrode for the detection of glucose oxidase enzyme being used to modify the rhodium doped carbon paste. As before, lactate was detected with lactate oxidase modification to the rhodium doped carbon paste. pH was detected with diazonium salt based chemistry. Here you can see that we have essentially conventional electrodes connected so that they can interact with the pore of this 3D printed microneedle array. You can see in this approach the detection of pH over the physiologic range of that analyte, glucose with a glucose modified carbon paste electrode over the physiologic range of that analyte, and lactate with a lactate oxidase modified carbon paste, the physiologic range of that analyte. Here you can see subsequent work involving detection of L-DOPA. In this case, 2 different approaches were used to detect L-DOPA, both enzymatic amperometric and a non-enzymatic voltammetric approach. And so we have the unmodified carbon electrode being used for the first approach, the voltammetric approach, and tyrosinase modified electrode for the chronoamperometric approach. And you can see here that these are 2 electrodes being used to detect the same analyte, L-DOPA, detecting them with the enzymatic amperometric and the non-enzymatic voltammetric approaches. And you can see here that basically one data from one electrode can be used to confirm the data from the other electrode. So this can be used to sort of monitor Parkinson's disease. This is another example of this approach. And you can see here again the idea of trying to use basically these two different approaches to basically confirm data from one approach using the other approach. Here you can see another example where we have 3D printed microneedle arrays being used for detection of fentanyl, opioid drug of abuse. And you can see here this is an approach involving a graphene ink. It's modified with an ionic liquid. Here you can see that chemistry involves uh, oxidative dealkylation of the piperidine tertiary amine in fentanyl structure. And you can see here that you have ability to, through this direct oxidation of fentanyl, get for detection of fentanyl, the limit of detection of 7.8 micromolar. Here you can see that the sensor works in the presence of interfering molecules such as ascorbic acid, uric acid, caffeine, acetaminophen, and theophylline. Here's another approach. This is with cholesterol oxidase. Cholesterol oxidase was modified, was used to modify a platinum working electrode. This electrode was then covered by naphthion. Naphthion is to enhance the electrode stability. And so we have a 3 electrode system where you have platinum, silver wires in your cholesterol oxidase. Modified platinum electrode that serves as your working electrode. You then also have, as we mentioned, the ability here to use screen printing technology to help trying to miniaturize the sensing platform. Of course, nowadays you have many potentiostats that are sort of built around screen printed chips. So in this case, we took advantage of this sort of recent screen printed electrode technology so that we could, in this case, use this 3D printed component, the screen printed component, along with the 3D printed chip, the basis of cholesterol detection. In this case, we use Prussian blue that's also electro deposited onto the working electrode to allow for electrochemical reduction of the enzymatically produced hydrogen peroxide. So here you can see we have these well-defined parograms for 1 to 9 micromolar concentrations of cholesterol. And you'll also see here that you have a detection limit as low as 0.5 micromolar based on the signal to noise ratio. And then subsequent work has involved machine learning. So using machine learning algorithms to help train and understand the data from this electrochemical testing. So one of the things we see here in the more recent study, again using these screen printed electrodes, we are able to then have machine learning to assist in the sort of understanding of the electrochemical data. Here you can see some of the newer 3D printed microneedles. And you can see here that we have now very sharp tips. In this case, you do have these hollow structures that will bring fluid to the to the sort of working electrode. Here you have a graphene modified screen printed carbon electrode that was created and used for lidocaine detection. we can see here that in fact we have good data for as you can see here, lidocaine concentrations between 5 micromolar and 120 micromolar that can then be used to sort of understand uh, sort of, we'll get to the later slides, but the overall performance and sensitivity of this approach. And here we can see the square wave voltammetric response in the presence of interfering molecules. You can see here that you don't have an overlap with the lidocaine spectra. Here you can see a little bit more data that was obtained in a sort of a human-like situation where you have a lidocaine solution, parafilm seal on top, and you apply the microneedle interface to that through the parafilm seal to interact with the lidocaine solution. So here you can see how machine learning can be used to understand the data. See here, your regression model was used to fit the experimental data to the experimental, was used to fit the experimental data, and it fit the experimental data very well with an R-squared value of 0.98. And so we then have a deployable web application based on this model, this linear regression model. And this allowed you to then input the peak current value obtained from square wave telemetry data. And you can see here that the lidocaine concentration predicted from machine learning was good proven with experimental data. Here you can see example of buprenorphine detection, where we have carbon-coated conductive microneedles that are then being used in this case for the detection of buprenorphine, which is used in opioid use disorder as a potential treatment. So you can see here a good linear relationship between the peak current and the buprenorphine concentration, or 2 micromolar to 140 micromolar values. You can see here that you don't have overlap of the buprenorphine curve with the curves of the potential interference like ascorbic acid, acetaminophen, uric acid, caffeine, or theophylline. Here you can see that the performance of the sensor was preserved for 80 at a level of 87% after 20 days in storage. So we also see here the calibration plot has relatively good linearity, good sensitivity. Our linear regression model, as before, showed in this case also a high value R-squared value of 0.98. Again, we put the current, and so you then have machine learning to provide us with the concentration, and we have the concentration, the current matching the known data. So that's examples of stereolithography being used for microneedles for sensing. And now I will finish with two-photon polymerization. The two-photon polymerization is a variation on stereolithography that involves the use of multiphoton absorption in order to create structures with features below the diffraction limit. So you can get features below 1 micrometer feature size. And in fact, some people have gone features down to under 100 micrometers. So with a home build system, you can tune various aspects of this polymerized part, including you can change the laser power, the exposure time, the distance between voxels, truncation amount of the voxel, the numerical aperture of the objective lens, so on and so forth. So what you see here is an example of a polyethylene glycol diacrylate structure polymerized with two-photon polymerization. And you can see here that the feature size being stair-step being 200 nanometers. And one of the things you can see here is that you can change the sort of dimensions of that ladder step by changing the average applied laser power. So this is one example of tuning one of these parameters you mentioned here, and you can get a change in the feature size. So we've polymerized a wide variety of parts using two-photon polymerization. This is an example of a microneedle device that we first created in 2006 with two-photon polymerization. In subsequent studies, you can see here, created different microneedles with different bore sizes and different heights with two-photon polymerization. Created out-of-plane microneedles where tip is out of plane with the bore. We've then created parts where you can see here, these are hollow microneedles created out of a polymer that contains urethane and acrylate components, so it's very fracture resistant. You can also create the microneedle and the bed on which it sits in a single step. And so you can basically create the platform, create these platform with holes in it, then polymerize the microneedles. We created examples of structures where this was demonstrated, where as you can see the bed on which the microneedles sit, sort of hollow structures in which the microneedles sit, and then the microneedles themselves are created in a single step. You can also use structures created through two-photon polymerization as master structures for, as I talked about at the beginning of this talk, indirect rapid prototyping. So you can see here examples of indirect rapid prototyping where the structure created through two-photon polymerization uses the basis for iron electroplating. See your examples of the structures created through that approach, including microneedles with sharp tips and a hollow bore. Here you can see that the polymerized structure is very flexible, and you can see here that the molds themselves are reusable. You can see here that the parts themselves can be used to penetrate skin. So you can now see here some examples of how two-photon polymerization created microneedles can also be used for electrochemical sensing. This is a porous carbon electrode created through laser interference lithography, the Q-switched YAG laser. It was then, you took that porous carbon electrode, then exposed it to this flutamycin containing cocktail. This then allows you to create this ion-sensitive electrode, has a high degree of porosity, and so you end up having a structure that has high sensitivity to changes in potassium ion levels and insensitivity to changes in sodium ion levels. So you take this ion sensitive electrode, you create that as the working electrode. You then have a silver chloride reference electrode, platinum counter electrode, connect this with a microneedle device, then run tubing to bring fluid from the bore of the microneedle to the 3 electrode setup. And then you can see here that you have a sensor that is insensitive to changes in potassium ion concentration. I'm sorry, insensitive to changes in sodium ion concentration and sensitive to changes in potassium ion concentration. So we have the ability to have this on-chip detection of potassium ions. In a similar sort of approach, in this case you have this gold working electrode that is created underneath a 3D printed microneedle created by two-photon polymerization. Then this sort of electrode array was modified to contain sandwich immunoassays to detect myoglobin and troponin levels. This involves horseradish peroxidase-based chemistry. And what we are able to see is that with this approach, you can do chronoamperometric analysis of the sandwich immunoassay with this setup, and you're able to get a 100 parts per billion, detection of myoglobin, 1,000 parts per billion detection of troponin. And these analytes are released in the blood after a heart attack or myocardial infarction. And the idea here is that you can, in fact, detect these at a very high level of sensitivity with this microneedle-based chip. As I mentioned before, you can also do this indirect rapid prototyping, and we've done that for drug delivery applications. One of the things that we did is to create replicas of the two photon polymerization, created microneedles to create replicas that were solid microneedles that were created out of a material that had contained acrylic and urethane components, so it was very fracture resistant. And you can see here, we tested this system with mechanical testing, a Electroforce 3100 system. We're not able to fracture these solid microneedles. We then created dozens of replicas of these microneedles with heights of 500, 750, 1,000 micrometers tall. So these are basically microneedle arrays of solid microneedles. So it basically creates an array of pores in the skin. And then we use this to create pores in the skin and then deliver a drug, amphotericin B, that's used for treatment of cutaneous leishmaniasis. And so we were able to then be able to decrease the lesion size for the cutaneous leishmaniasis with this approach based on these 3D printed and then molded microneedles. We've also looked at tissue engineering scaffolds. So here you can see an example of a scaffold created through tissue for tissue engineering with a 2-photon polymerization approach. This is created out of organically modified ceramic. So you can see here B35 neuroblast-like cells attaching to these scaffold pillars. These pillars, as I mentioned here, are 75 microns in diameter, 20 microns tall. You can see here these B35 neuroblast-like cells attaching to these pillars. You can see your subsequent work to create various structures for tissue engineering. This is a urethane-based elastomer that was created through 2-photon polymerization. You can see here a replication of a cylinder motif. You can see here atomic force microscopy was used to examine the mechanical properties of this scaffold. It has Young's modulus of 96 kilopascals, so it's a very flexible, soft material. You can see here when you look at human bone marrow stromal cells, you can see here that it has good cell viability similar to that of tissue culture polystyrene. You can see that cell seeding and cell attachment on a 3D printed surface are similar to that on a flat surface. You can see here a 3D printed sort of structure placed in these wells. So these are all 3D printed structures placed in these 96 well plates. You can see here, you can study the cell growth within these porous scaffolds. And certainly you can see sort of stretched out structures with focal adhesions within these cylindrical structures. You can also see higher amounts of protein adhesion to the surface. So you can see here with the BCA assay, much higher amounts of protein adhesion to a 3D printed surface versus a flat surface or the tissue culture polystyrene surface. You can also see that you have higher cell viability rates. One of the things that you can notice is that the higher cell viability rate is probably related to the fact you just have a much larger number of cells spread over a 3D printed 3-dimensional surface versus a flat surface. We've also, as I mentioned, looked at these inorganic, organic hybrid materials or ormesser materials. This is an example of an ormesser material that contains zirconium propoxide and methacrylic groups, was polymerized with Michler's ketone as the photoinitiator. You can see here examples of where an array of line motifs was generated with this approach. And you can see here that you have good control over the morphology of these features. So you have good reproducibility of these various lines within these 3D printed structures. This was used for to study the attachment of bone marrow stromal cells. You can see here good alignment of cells to these linear motifs within scaffolds. Here you can see that some examples of 3D printed structures where you have hollow cylinders of 250, 200, and 150 micrometers in terms of the inner cylinder diameter. Again, this is an inorganic hybrid material with contains zirconium-based inorganic component. And you can see here that, in fact, if you have the smallest cylinder diameter of 150 micrometers, you end up having higher amounts of calcium deposition and higher amounts of cell seeding. You also will see here the very interesting change in terms of the mechanical properties of the materials. In fact, if you look at the material that's aged in water, either in water for 7 days or ethanol in 7 days, you get this dramatic increase in the Young's modulus and the hardness. And this is related to the fact that you're probably getting desorption of some of the non-cross-linked organic components over time, whether it's in water or in ethanol. So we've done some studies looking at aging of materials in water to try to see if you can see changes in performance. And one of the things that we noticed is that if you age a material in water for 7 days, for example, if you age the material in water for 7 days, this is a polyethylene glycol diacrylate hydrogel material polymerized with Micheler's ketone. The extract taken from the earlier days had some cytotoxicity, but if you look at the extract taken from later days, there's much less cytotoxicity. So if you age these materials in water, you can desorb this unpolymerized material and get material that's much more biocompatible. Here you can see the similar study with polyethylene glycol diacrylate polymerized with ErgoCure 2959, which is a common photoinitiator. You can see the material aged in water for 7 days was not toxic. So that shows by aging these materials polymerized with conventional photoinitiators, aging these materials in water can get to a material that's not toxic. Another way of trying to get to a more biocompatible material is by using a bio-based photoinitiator. So this is an example of where we took a combination of riboflavin and triethanolamine and used that as the basis as a photoinitiator for polyethylene glycol diacrylate. You can see here that we were able to polymerize these scaffolds with this combination of riboflavin and triethanolamine as the photoinitiator. You can see here good feature-to-feature uniformity in these polymerized structures. You can see here that this material is very friendly in terms of genotoxicity studies. It has the lowest genotoxicity, has the genotoxicity similar to that of glass, much less than the genotoxicity of conventional photoinitiators. You can also see here good amounts of cell proliferation. These are bovine aortic endothelial cells. Good amounts of polymerization of cell proliferation of bovine and aortic endothelial cells on all of these scaffolds, including the one made with the riboflavin-based photoinitiator. And then if you look at the structure, you have a high number of living cells, low number of dead cells, the polymerized scaffold. More recently, we started looking at allylated gelatin, polymerized in this material with a ruthenium-based photoinitiator. So we have some recent study that we've published with University of Otago, showing that this material, ruthenium-based photoinitiator, has a very high time to gelation, as you can see here, as compared to the other materials. So much faster time to gelation, and it's a very good photoinitiator, as you can see here. You can get these large polymerized structures, and so this is one other class of materials we were looking at. So to close, we have overall a challenge with 3D printing in medicine. Once you get to a large number of parts, injection molding or conventional manufacturing techniques become more cost efficient than 3D printing. At the same time, you have to think about various sorts of compliance issues. You have to think about how the chemistry, phase, and crystal structure are varied throughout the structure when you're 3D printing. How does porosity affect the mechanical properties of the part? Are there any contaminants like unpolymerized material that affect the properties of the part? You also can see here the many challenges in terms of 3D printing, in terms of trying to convert the patient data to the eventual 3D part. So future opportunities include trying to develop new synthesis, characterization, modeling capabilities, expanding the number of inorganic and organic building blocks, understanding the lifetime of polymerized parts, their short-term toxicity, their long-term toxicity, and their breakdown products, reducing the processing costs, reducing the equipment costs, and increasing throughput are important engineering considerations. And then finally, you can see here this slide where we essentially took a hologram generator to for multi-focus 2-photon polymerization, thereby creating multiple beams from a single laser source. This created 4 daughter beams from this single laser source. So you could polymerize this microneedle array basically 4 times faster than just by using a single laser source polymerizing each of the 36 microneedles. So this shows you a way of trying to reduce the processing time through laser hologram technology, multifocus technology, and potentially other mechanisms can be used to reduce processing time. So I'm at hour 30 minutes. I'd be glad to answer any questions. Thank you for your time.
Thank you, sir. Thank you for your wonderful session, sir. Dear participants, do you have any questions? Kindly comment in the box. Uh, I think no questions regarding the session, sir. It is a wonderful session, sir. Thank you for the wonderful session, sir.
Yes, it's nice meeting all of you. Thank you.
Yeah, thank you. In
Bye.
future, we will do like this, and also in future we are plan to conduct one conference. Also, we will expect this kind of informative session and your participation in that conference also, sir.
Okay. Thank you for the invitation. Nice talking with all of you. Goodbye.
Thank you. Thank you, sir. Thank you. Thank you. Okay, dear participants, thank you for your patient attention.